All right, here is the quick version of section 4.1 from OpenStax PreCalculus. We're going to learn about exponential functions here. So a good place to start, maybe the most important thing is to know what an exponential function is. It's something that looks like this. So something that looks like this, in place of a and b are numbers. Specifically, in place of a is any number that's not 0, and in place of b is any positive number that's not positive 1. So lots of different examples you can come up with. I don't know, f of x equals, I think in the other video I did 3 times 2 to the x power. It's a perfectly good exponential function. Recognizing an exponential function is looking for something that looks like this. Note that sometimes this 3 won't be here. It'll be like 1 times 2 to the x power, in which case you wouldn't write the 1. So it's just 2 to the x power. That's still an exponential function, just playing the role of a is 1. Wait, I thought a couldn't be 1. No, that's b that can't be 1. A can be 1. So this is an exponential function, most easily confused with a polynomial function. The big difference there is with a polynomial, or a monomial perhaps, the variable is down as the base, and the exponent is a constant, is a number. Whereas here with an exponential function, the variable, the x, is up in the exponent. So that's an exponential function. The a and the b in an exponential function have meaning. This a right here, it'll turn out, is the y-intercept. It's the value the function takes on when your variable equals 0. And I can prove that to you, or you believe me when I say that, if I tell you that anything raised up to the 0 power equals 1. Right, so if I put 0 into this function, or this function for that matter, if I figure out what is f of 0, well, that'd be 3 times 2 to the 0 power. But 2 to the 0 power is just 1, so I just get 3. So when I put 0 in, 3 comes out, and there's nothing special about the 3. When I put 0 in, whatever number is written right here will come out. Well, the number written right here is represented by the letter A, so the letter A is my y-intercept. The letter B, I don't have a great name for it. Maybe I'll write this, even though this is probably a bad idea. It's kind of like the slope. So when I say slope, I'm talking about, remember in chapter 2 when we talked about linear functions, and we had y equals mx plus b. The a here is kind of like the b there. Super confusing because you have a b here. The b here is kind of like the m there. The only difference is that the m is how much you add to your y value every time x increases by 1. The b is how much you multiply your y value by every time x increases by 1. So kind of like slope, except multiplicative. So I can show you that. If I was trying to figure out f of 2, for example, I'd be figuring out what is 3 times 2 raised up to the 2nd power with this same function. So really what I'm doing is I'm starting out with 3, my y-intercept, and then I'm multiplying it by 2, and then I'm multiplying it by 2 again. So each time x increases by 1, from 0 to 1 to 2, I multiply by 2. So what I'd end up with in this case would be 12. I guess maybe this is worth talking about. Be careful with your order of operations. The exponents comes before multiplication. So don't do 3 times 2. Do 2 squared and then multiply by 3. And you get 12. Some things that end up being a little bit interesting are when you have negative exponents. So f of negative 2, for example. To figure that out, you must know that a negative exponent means take the reciprocal of. So instead of 2 to the negative 2 power, I can have 1 divided by 2 squared. And 2 squared is 4. So I have 3 times 1/4, aka 3/4. So when you have negative exponents, you have to know that rule for negative exponents. When you have fractional exponents, it helps to know that when you're raising something to a fractional exponent, you're involving roots. So in this case, I would have 3 times, and then this 3 in the denominator tells me I'm taking the cubed root of, and then 2 squared is equal to 4. So in this, f of 2/3 would be 3 times the cubed root of 4. So those are really the two tricks that you have to be careful of, negative exponents and fractional exponents. So I think I've talked about a and b. I've talked about evaluating some exponential functions. That's what we've been doing here. Finding the equation when given 2 points. Here's something that'll pop up a fair amount. Let's say I have an exponential function and it goes through the points 1, 6, do the same example I did in the other video, and -2, 3/4. And I'm told this is an exponential function, and that's important. So similar to how if you were told it was a linear function and you're given 2 points, you could use point-slope form. Same basic idea when you have an exponential function and 2 points. There's a way to figure out the equation. But it's a little bit tricky, so I'm going to go through an example here. We'll do more examples when you go through the book. The trick is dividing equations. So you take these points and you plug them into an arbitrary exponential function. All I mean by that is change the x and the y into 1 and 6 and leave the a and the b alone. Do the same thing here. You get 3/4 is equal to ab to the negative 2 power. And now you have these two equations right here. But you have two unknowns, which is kind of hard. Well, there's a way to solve when you have two equations and two unknowns. Actually, there's lots of ways to do it. A trick that'll be really handy is dividing equations. So yes, you could solve one of these equations for one of your variables and plug it into the other one. That'd be algebraically cumbersome. An easier way to do it is divide the equation. So 6 divided by 3/4 must be equal to ab to the first power divided by ab to the negative second power. And why does that help? Well, really the reason it helps is these a's cancel out. So I get this mess over on this side, whatever that simplifies to, divided by this mess over on this side, whatever that simplifies to. But the nice thing here is I only have one variable, the letter b, that I have to solve for. So I can do that. 6 divided by 3/4. Well, probably the easiest way to do that is the way you divide fractions is you multiply by the reciprocal. So it's the same as 6 over 1 times 4 over 3, which is 24/3, which is just 8. And that's equal to, this is b to the first power divided by b to the negative second power, which I could rewrite as b to the first power times b to the second power, because the negative exponent means take the reciprocal of it. So since it's down on the bottom now, I could put it up top if I made it a positive exponent. And then b to the first times b to the second is b to the third. You add the exponents. Another way you could get there is at this stage, you just subtract the exponents. 1 minus negative 2 is positive 3. And if 8 equals b cubed, then b must be equal to 2. You're taking the cubed root of both sides of the equation there. And if you know that b is equal to 2, you choose one of these two equations, whichever one you think is easier. I'm going to choose this guy. And you change all the b's into 2's. Okay, 6 equals a times 2 to the first power. Wait, so 6 equals 2a. Doesn't a just equal 3? Sure does. So now you have your function. I guess if I'm going to say it's a function, I should write it in function notation. F of x equals a times b to the x power. Same thing I've been dealing with up here. These will be useful tricks, so I wanted to go through this. You'll see more examples if you go through the chapter. One note before I go on is that if one of your 2 points has an x-coordinate of 0, you're being told the y-intercept. But wait a minute, the y-intercept, I remember that. That's just a. Yup. So if I gave you 0, 5 here, for example, that would tell you that a equals 5. And that would significantly cut down your work. You could just take the equation from the other point and change the a equal into 5 and solve for the other letter, the b. But since that's the easy example, I decided to do a hard example. That easy example you could do with this same method if you felt like it. There's just shortcuts you can also do. Before I end this video, I want to show you a couple of formulas. So maybe I'll pause this and write those down. Okay, let's finish up this video with a couple of applications of exponential functions, a couple of places where exponential functions kind of pop up, or in real life, I guess, if math isn't real. It's the compound interest formula and the continuous growth or decay formula. And they're both given here. So really the takeaway, I guess, is just these formulas and understanding how to use them. But the point that I want to make is these formulas, which maybe you've seen before, are really examples of exponential formulas, exponential functions, I guess. Playing the role of a is this p right here, and playing the role of b is this 1 plus r over n. And playing the role of x is this n to the t power in some sense. And then sort of similar over here, we have these exponential functions because we have our variable up here in the exponent. And the way these make sense, I don't know, the way I remember this, I don't know if this is 100% true, but I'll pretend it's true, is thinking about a simpler case. If n just equals 1, so let's do some arrows here. If n equals 1, then this formula just boils down to a of t is equal to p times 1 plus r to the t power. And this makes sense, at least it makes sense to me if you look at it with an example. So let's say you start out with $100 and your interest rate is 20%. And you might want to figure out how much money you have after 1 year. Well, I could figure that out. I could say, well, a of t in that case would be equal to 100 times 1.2 to the t power. And what I'm being asked is to figure out what is a of 1. So it's 100 times 1.2. In other words, it's $120. And so what's going on here is the 100 is how much you start out with, and then you're multiplying by 1.2 a certain amount of times. So if t were equal to 3, I'd multiply by 1.2 times 1.2 times 1.2. I'd multiply it times 100 3 times. So that's kind of the exponential aspect of this. So what's going on when n is not equal to 1? Well, if n equals 2, for example, I can do this exact same example. I'll use these same values even. I get a of t is equal to 100. And then instead of 1 plus r, it's 1 plus r over n. So instead of 1 plus 0.2, it's 1 plus half of 0.2. In other words, 1.1. And now I'm raising it up to the 2t power. So if I want to figure out what is a of 1, what I have to figure out is what's 100 raised up to 1.1 squared. And it turns out this is not 120, this is 121. Turns out you end up with more money if you're compounded more frequently. And the reason that works out is because you're earning interest on the interest, right? You want to get all 20% eventually, but if you get it in 2 chunks of 10%, you make out better. Because when you get the first chunk of 10%, now you're up to $110. When you get your second chunk of 10%, it's not $100 that's getting that next 10%, it's $110 that's getting that 10%. So you get interest on the interest, you get an extra dollar here, you end up with 121. So the point here is there's this continuous interest formula, it's this guy right here, and depending on how many times you compound, you have different formulas, which is the number n here. And it's to you, if you're the investor, benefit to have n be larger. So maybe instead of n equaling 2, I should have n equal 100 or 1,000 or 1,000,000. And you might think that that just keeps getting you more and more money, and eventually you'll end up with infinitely many dollars. Well, it's not actually true. It turns out that converges. You can never get too much more than 121. And the other example actually worked it out. I think we ended up with like $122.50, something like that. The idea is as n goes towards infinity, if we compound continuously, then this formula turns into this formula right here. That this number e arises. E for our purposes is just some number that's about 2.7. That's all you have to know about it. Turns out it's a really special, it's a perfect number, but I'll get more into that in another video. But that gives us this continuous growth rate. So if you're not told how many times you compound, you're instead told you compound continuously using this formula right here. Everything else is the same. P is still P, R is still R, T is still T. It's just now you have this E floating around. You're like, what? I'm looking at my problem and trying to figure out what to plug in for E. E is not something you're looking for. It's not a parameter. It's a number. It's this number right here. One comment is your book uses a little a here in place of this P in this formula. I think it's easier to use P because it stands for the initial amount, so I like to be consistent between the two formulas. Just an FYI thing. I think that's about all I have to say about this. So maybe I'll wrap this up here and call this good.